Welcome to the 16th lecture on aqueous corrosion and its control. Now we are discussing on the galvanic corrosion part 3, right. We are looking at the galvanic corrosion, correct. Now after looking at the electrochemical parameters that govern the galvanic corrosion, we need to look at overall factors which can influence the galvanic corrosion of dissimilar metals. Okay. So, I term it as factors affecting galvanic corrosion. The more obvious one is the nature of the environment. The second is location of galvanic attack. The third, we are using two different metals, two different structures having different chemistry, different electrochemical parameters, and the area ratios are very relevant, very important. Okay. Area ratios of anode and cathode. So, we shall go in details and try to understand. If you understand the factors controlling galvanic corrosion, it will be much easier for you to devise means of controlling the galvanic corrosion. So, that is the whole basic idea of analyzing the factors those can influence the galvanic corrosion. Let us start with the nature of the environment. We can say the severity of the environment it increases, the galvanic corrosion also increases. The vice versa is also true. If the environment is quite mild, then the galvanic attack becomes relatively slower. Okay. Now, we can have just few illustrations to demonstrate how the severity of the environment is going to be influencing. I give two examples. One is the corrosion in magnesium sulfate, which is relatively a mild environment, and corrosion in sodium chloride solution, which is relatively a severe environment. Okay. And take the two metals which are steel and the zinc. If you can look at the corrosion rate of these two metals in uncoupled conditions and galvanically coupled conditions, you will see how the corrosion of the zinc, which is more active, would change significantly if the environment becomes very severe. This is a data taken from the Fontana book. You can just have feel for it. Let's take the case of 0.05 molar magnesium sulfate. Zinc virtually does not dissolve and corrode, steel corrodes. When you galvanically couple these two, you notice that zinc corrodes at a higher rate and steel in fact shows a marginal improvement in the weight, in fact the weight gain. But you notice that the weight gain is not because of growth of steel, growth of iron. It primarily happens because when you make a metal cathode, the pH goes up and some deposition occurs. So if you clean them up, you would not see there is any significant increase in the corrosion rate. So this rise in the weight is not anywhere related to the metal deposition here. As opposed to this, you take molar NaCl solution, both the steel and zinc corrodes. See, both corrode, in fact the corrosion rate is almost the same, primarily because it may be diffusion controlled, right. The diffusion control, it does not depend upon the corrosion tendency of a metal, right. In the coupled conditions, you see that zinc corrodes at much higher rate and steel, it does not corrode at all. So, the corrosion rate of the active metal here, I mean relatively active metal here, the zinc, is very much dependent upon how severe the environment is, and the environment here, sodium chloride, proves to be very aggressive in nature. There are also cases where the galvanic tendency of the metal changes if you change the temperature or concentration. It is possible that at a given temperature and pressure or a concentration, one metal acts as active, other one acts as a noble. Slightly change the temperature, the metal which is active turns into a noble metal. These things are having practical relevance, importance. We give some examples. Let us take the case of steel versus the zinc here. And all of us know that galvanized steels and the zinc coated zinc, it sacrifices and then steel is getting protected, right. But if the temperature of the coating is increased, if the temperature goes beyond 80 degrees Celsius, zinc becomes noble and iron steel becomes active, and this is called as galvanic reversal. Such a phenomena has practical problems. One is, we have seen that the galvanic corrosion of steel, if the steel is galvanized steels, what does it mean? Here steel corrodes. One more example which is relevant, we will discuss a little later actually, is application of zinc as sacrificial anodes. in a cooling water system. Not possible beyond 80 degrees. Why? The zinc starts passivating, it loses its protective nature, in which case you may have to use magnesium, or anyway zinc is not going to work. There are few more examples which is in fact very interesting. You take tantalum and platinum. This is a passive system. This is, let us say, sulfuric acid, right, and you do not see no galvanic current. Okay, until 110 degrees Celsius temperature of the sulfuric acid. You have no problem, you can have platinum and tantalum coupled together, you do not give any galvanic corrosion rate at all. But if you rise it above or equal to 265 degrees Celsius, okay, and tantalum corrodes, and you will see a galvanic current of about 100 milliamperes square feet. The tantalum turns into a active metal. The galvanic corrosion was not operating at all. As one more practical example is, the tin coated steel containers for storing the food, right, it is a beverage cans, okay. If the food, I mean, if someone, let us say juice, for example, orange juice or apple juice, it decomposes and gives rise to organic acid, it attacks tin complexes, the tin becomes active. Otherwise, tin is a noble metal, right, compared to steel, okay. That is not going to work. Now steel, I mean, your tin starts corroding because of the complexing of this actually, okay. So such kind of galvanic reversals are of importance in industries and should be taken care of or should be studied very well before you select the system. Let us look at the location of the galvanic attack. Take an example, yeah.
There is a reversal in galvanic content.
In which case, see
Why is the reversal occurring with increasing temperature?
Oh, in the case of tin, in the case of zinc you are talking about? Yeah. See, you take in the case of zinc, okay, you raise the temperature, the zinc forms a nice adherent zinc hydroxide, zinc carbonate, which are somewhat similar to passivation. And you know that when the metal is passivation, the corrosion potential moves up, the corrosion rate drops. Whereas at high temperature, steel does not get protected, it does not form a protective oxide film, okay. So the corrosion potential of zinc becomes higher compared to the corrosion potential of steel, because steel does not form any passive films. Please understand, the galvanic corrosion depends primarily on ECAR, it does not depend on corrosion rate at all. The first and foremost condition is the potential difference. The Tafel slope, exchange current density, all of them are important, But if the potential difference between these two metals do not exist, then there will be no galvanic corrosion, or the one which exhibits a relatively active corrosion potential will act as an anode. Okay. So, the potential what happens? So, surface changes would bring in this kind of effect. Tantalum is a similar situation. Rise the temperature, sulfuric acid, the passivation is no more stable, it just goes away. Tantalum is one of the reactive material, right? How does the corrosion resistance for tantalum affected? Somewhat similar to stainless steel or titanium alloys. In fact, better than titanium alloys. The oxide film is very stable, okay, and that is why tantalum is used in most aggressive environment, although it is very expensive. But oxide films are kinetic resistance, right? If you rise the temperature, the film breaks, the film dissolves, and so the galvanic reversal occurs in this case, right? Okay, yeah, thank you for the question. Let us look at the location of the galvanic attack. It has a very important relevance for us actually. Okay, let us take an example of, let us say, a copper. You have a steel and it is exposed to the environment. And you know that this is the anode, right? And electrons move like this, and there is going to be maybe H plus or oxygen, whatever comes, and hydrogen is getting liberated. Agreed? This is what happens. Now you tell me, where will the galvanic attack be severe in this case? The most severe, yeah, at the interface, right? The galvanic corrosion will be more severe at the interface. Why it is more severe at the interface? The answer is correct, but why is it more severe? You consider. The potential difference between this point and this point remain the same, that is going to be almost independent of that, okay. What more is coming to picture here is the resistance offered by the electrolyte, right? The resistance offered by the electrolyte. So the current flows like this, what? Electrons flow this way and current flows in the electrolyte. So if the current has to flow from this end to the other end, farmost end, the resistance increases, the quantum of current that reaches this place will be less compared to the quantum of current that reaches to the interface, because the resistance, it depends on what? The resistance depends upon the rho L upon A gives you the resistance. The resistivity of the electrolyte, the length over which the current is going to flow, of course area which the current is going to flow, cross section over which the current is going to flow, related to resistance. So as this the distance increases, the quantum of current that is going to flow reduce. So the amount of current corrosion is going to be decreasing from this point to this point. So that means if the resistivity of the electrolyte is increasing, what is going to happen? Assume that there are two electrolytes, one with a higher resistivity, the other with the lower resistivity, and you will see the attack, and what kind of attack difference you will find. The same copper and steel, one with a higher resistivity, other one with lower resistivity. What kind of differences do you see by just observing them? That is true, but between the two,
the resistance is higher in the electrolyte, in that case it will be higher.
yeah. So when the resistivity is more, the localized attack is more, and the attack is confined to the interface, right, more than the attack at the interface phase becomes high. In fact, this is one of the characteristics of galvanic corrosion. Okay? If you want to diagnose a problem, if you see in the industry that there are two different set of metals which are erratically shorted, and you want to show that there is a galvanic corrosion, the first criteria is that what? The interface should have a deeper attack. In fact, attack will be something like that. This is your active metal, your relatively noble metal, right. On the other hand, assume that I have pipeline, and pipeline I got there are two different metals in the pipeline, okay, and I have a pipe. So one side is relatively active, other side is relatively noble. The fluid is going inside and it is corroding. If the corrosion is away from the interface and is severe, would you call it as a galvanic corrosion? And it happened in the active metal, right? Would you call it as a galvanic corrosion? Do you get my question? The pipeline carrying of corrosive fluid, the pipeline has got two parts. Part 1 is active metal, part 2 is noble metal, and they are erratically shorted as interface. The pipeline leaks. You found that the leak has occurred at the anodic member of pipeline. But you also notice that the leak is not at the interface, it is about 10 centimeter away from that, okay, or 5 centimeter away from this. Would you call that as a galvanic corrosion? You have to give an answer. Why do you call it galvanic corrosion then? Yeah? Yeah. If the resistance is offered, then you should be confined more towards, when you say resistance means what? Higher resistance. Then you should be more confined to the interface. Huh?
If there is a resistance, but still corrosion is occurring. So the liquid is moving.
Yeah, liquid is moving. That's what the problem we get in industry, right? So what do you think? If the corrosion has to occur by galvanic mechanism, there is no other way but the interface has to corrode at higher rate. Is there any other way you can do that? When the resistance of the electrolyte is of the electrolyte increases from the cathode to the anode, has to move away from it, the current will not flow more. Do you expect current to flow more at a higher distance and less current at the interface? The physics does not permit. It has corroded, no doubt, but it is not due to galvanic corrosion at all. It cannot happen. You need to diagnose what the problem is. There may be other form of corrosion that has happened, but yes, certainly it is not a galvanic corrosion. Okay. So it is very important that you need to know the fingerprints, you need to know the characteristics of the corrosion failure. The characteristics of corrosion failure is, it happens with the active metal, it happens more at the interface. If it happens, for example, at the noble metal, you would not call a galvanic corrosion. Maybe erosion has taken place. Metal may be noble but is softer, it happened. Maybe there are some microbial corrosion taking place. So, it is very important that you need to understand the fundamental and then try to relate to the failure. It cannot be having a conflict with the basics. Okay. So, it is not really a galvanic corrosion, in which case it may be different. Then you need to diagnose and find out the root cause, why the corrosion has taken place there. This is in fact is a fingerprint of galvanic corrosion. The environment is less severe, the groove attack becomes less only. But you cannot say that corrosion occurs far away and so there is it is a galvanic corrosion. Let us go into the next important aspect of it, the area effect. It is very easy to understand and it is a very impacting in designing structures to avoid galvanic corrosion. Let us look at the mixed potential theory and see whether it helps us. We know that total cathodic current is equal to the total anodic current, right? It cannot really change. Now, what is this? Is equal to what? This is equal to current density multiplied by the area of the cathode is equal to, right, current density at the anode and area of the anode. Agreed? Okay. You know what it is, right? A represents what? A represents area. Okay. And other variables that you are aware of, right? Let us rearrange this equation, equation 1, equation 2. See. What do you understand from this equation? Yeah? If the area, if the cathode, area of the cathode becomes very high, the corrosion current density on the anode is going to be high. So, that means you can say that if a cathode tends to become infinity, IA is going to tend to become infinity. When I say IA here, I mean the increase in the corrosion rate because of galvanic action. On the other hand, AA tends to become infinity, IA tends to become 0 due to galvanic couple. Understood? So, what does it really mean in practice? If you are an engineer, you want to construct certain component, what should be the design criteria? Yes, you should take care that the component you are thinking about, you are choosing a material, you have to choose two metals, you have no choice but to do that. Should always ensure that the anode is larger and the cathode is smaller. The vice versa could be a real problem, okay. And this can be also seen by the mixed potential theory as well, okay. Let us look at the mixed potential theory, see whether it is correct or not. I am putting log capital I here I am not using here small I, capital I means what? Current, right, okay, and assume that this is steel, and so it is ion going as Fe2 plus in acid, right. And I have the area ratio of iron and platinum are equal to 1. I am not showing the cathodic curve corresponding to steel because the hydrogen evolution on steel is lower compared to hydrogen evolution, or you can show it here, it is okay. I naught H plus H on steel, okay. Then you can use platinum, right. This is area ratio is let us say is 1 centimeter square, steel, platinum 1 centimeter square, steel, okay, 1 centimeter square. I make platinum, it's about 1000 centimeter square. When I make a 1000 centimeter square, you can please make I think it's a small change here. You cannot make this I naught here, should be capital I, okay, because we are talking about the area, we are not talking about the normalized, we are talking about actual current, right. So if you are going to have multiply the area of that, it's going to be like this, okay. This is 1000 times the area, okay. So the corrosion rate would increase because of the galvanic action. And this has some practical implications, and I just repeat the illustration given in Fontana's book. It is not too concentrated, but it is isn't reasonably concentrated sulfuric acid. See, very highly concentrated sulfuric acid, okay, you do not need anything. The steel offers very high resistance to corrosion, but moderate concentration and dilute dilute acids, the steel corrodes heavily in sulfuric acid. So how does the steel becomes resistance to corrosion? You apply a coating, you call a lining actually, right. You give a epoxy lining. The difference between a lining and a coating is the following: the coating is normally given in order to prevent the corrosion of the metal, but the lining is given not only to prevent the corrosion of the metal, but also to see that the product does not contaminate, right. So, you may allow metal to corrode, okay, because you can replace it, but if the sulfuric acid has got too much of ion corrosion products, there is no use. So, the lining is generally meant to prevent corrosion to the extent that the corrosion products, they do not contaminate whatever process fluid that you are talking about. Now, initially a steel tank was used, and they had this was the epoxy lining, this is sulfuric acid. It is working well, okay. It gave us to few years of service, okay. there is no problem. But what happens, no, there is always a mechanical damage, people want to clean the tank. So, when you start cleaning the tank and the bottom of the tank more often suffered the corrosion, okay, severe corrosion, but lasted for a few years. Seven, 8 years it lasted. And they found that the corrosion is more often on the bottom, is more due to mechanical damage due to corrosion damage. They thought that they can line this tank with stainless steel. Stainless steel is harder and mechanically it is quite sound, and you do not have to worry about mechanical damage. When they want to do a lining of stainless steel, then they thought, okay, let us not line completely the tank because it costs more. See, many of the tanks are very, very big, right? You can save money by reducing the lining, and it is happening anyway only at the bottom of it. So, they started giving a lining in this manner. They gave a lining to this, and the top portion, the steel, and it was a steel, the tank, and it is coated. It is not really well drawn anyway, it is a paint. This is painted. How do you line it? And this is a place you weld, right? Welded, and you can see, okay, you can make it a little more neat. This is stainless steel lining. Stainless steel lining is done. Interestingly, this is sulfuric acid. Now, tank failed. Very shortly. And it failed where? Failed at the weldment. Okay. Now, you see here, you spend stainless steel, very high expensive lining. Despite that, the life is very short. Very interestingly, the guy diagnosed saying that the painting is bad, and so the tank failed because the painting occurred, the corrosion occurred at the paint, and this place is welded here, right? And you weld it, and painting is always difficult at the painted location, right? Normally you grind very nicely and then you paint. So the person said that, oh, the failures happened because of the improper painting of that, and they went on to say that we should redo the painting. But some wisdom prevailed and tried to look at why it is failed, why it failed. Before I go into that, answer. Can you anybody guess or find out why it does happen?
There is a small failure in paint, the area of the anode will be very small as compared to the large area of the anode.
Fantastic. Okay. The paint can never be impervious, always porous. When the paint is not impervious, it is porous. Now what happens? There are very finite place, small locations, you have an anode. Not only that, you have a lining which is stainless steel lining, which is a cathode. That cathode is of infinite area compared to very finite anode below the coating defects. So, very highly accelerated corrosion taken place, right. So, the reason is simple. What is the reason? The reason is, okay, defective coating, then what happens? You have AC upon AA tend to becomes infinity. Why it failed? So, there are several such cases why coatings ought to be given. Only on cathode if you cannot coat both, right, or you coat completely. Suppose had the guy has coated completely both the anode and cathode, then what happens? There are defects in the paint coating, the cathode also very small in number, right, small in area, no problem. So, this leads to the understanding that if you have dissimilar metals, you coat both the anode and cathode. If you cannot coat, then what happens? We coat only the cathode. So, if you can coat only the cathode, then what happens? Then you will have a very finite area of the cathode. The galvanic corrosion becomes very minimal and you would not have any problem at all. So, coat both anode and cathode, or if not possible, coat only the cathode and not the anode. So, such kind of surprising conclusions that will come out of understanding of the parameters affecting the corrosion. Okay, so we have seen now the factors affecting corrosion, and I think you should be able to now find out or able to propose how to prevent or mitigate galvanic corrosion. Yeah, I want a very quick answer. Quickly you should move forward. Yeah. How do I mitigate galvanic corrosion? Yeah. Avoid use of dissimilar metal, that is simply not possible. Okay. Many cases you have seen in the case of heat exchanger, not possible. If I have to use, then I use what the first criteria. What do I see? Look for first. I look for anodic area, I look at it. But if I can choose metals, yeah. So I look at the galvanic series, right? I look at the galvanic series. Okay. Metals closer in the galvanic series. What more I do that? Yeah, I can also look at higher anodic and ratios, okay. Where it's possible, you can look for higher anodic to cathodic area ratio. Then what happens? I can isolate electrically, right? I can insulate electrically. Please look at where possible, it may not be possible everywhere, okay. What else I can do? Coating, right? Coating. It's an important lesson here, right? What is the lesson here? Coat? Yeah, both, coat both anode and cathode. If not possible, coat the cathode. So, we also had one more lesson in terms of effect of environment on galvanic corrosion. What is that? More severe is the environment, more severe will be the galvanic attack. So, how do I reduce the corrosivity of the environment? Yeah? Yeah, what is that? Inhibitors, right? Use inhibitors. They are done, huh? In cooling water systems, people add inhibitors. What more you can do? Yeah, you can use the third one, use the third metal, active to both. This is used much in industry. This is done mostly in industries. I just given this figure you've seen before, right? And it's an heat exchanger. This is called as header or water wall boxes. Header it is. These tubes generally are stainless steels. There is a galvanic corrosion here. How do I control galvanic corrosions? You can, in these places, you can use zinc anodes, okay. When I weld these places with the zinc anodes, what happens now? The steel, though active to stainless steel, it is rendered noble with respect to the zinc. So, zinc corrodes. So you a couple of years, no problem, okay, and you can replace the zinc anodes periodically, and it is done in industries, okay. It is not uncommon, it is done, widely practiced in order to reduce the corrosion of the active metals, okay. It is done. So, use a third metal, that means you have, okay, this is your cathode, so anode. What happened? You are going to use A1, and A1 is anodic to A, and C is what? C is a cathodic. So you can replace this A1 all the time, right? Whenever you find this anode is dissolved. So it's a sacrificial one, okay. You can also do one thing, you can also, make this anodic parts easily replaceable. You can design that, right. You please notice we have given some 7, 8 like this, right, 6, 7. Not necessarily all of them will work, depending upon the particular application. You may use a combination of 1 or 2 or 1 or more. The idea is that the cost brings down and there is a reliability, safety in the system, okay. So, that is an engineering aspect of what kind of technique can be used to avoid the galvanic corrosion of metals. So, we are talking about mitigation. Let us go to the last important one, that is how do you test for galvanic corrosion. So, what are the testing that you would like to do? The most simple test, what will be that? I just give you two metals, I want to know if they are compatible or not, or I give you three metals, you find out which are the two are most compatible. I want to do a very quick test, okay. What test will be useful? You studied all of them, all parameters and all. Three metals are given to you, or I have given you, let us say half a dozen metals are given to you. You do not have much time. I just want to choose two of them. Otherwise, all six of them are satisfy the requirements, like whatever requirements I want to choose. Yeah? Yeah, first of all, you can determine the galvanic potentials, right? This I call it as ECAR actually, okay, ECAR. In a given environment, you just measure it, right? You choose those two metals which lie close in ECAR values, right? So, ECAR is one important parameter, but it does not give you the corrosion rates, right? It does not give you corrosion rates. So, you want to determine the corrosion rate in the galvanic systems. What parameter do you use? Will ICAR of each of them will work? Will it work? I give you ICAR of metal A, ICAR of metal B, will that be useful? You think can use that? Yeah? Would that be useful? Not useful? If useful, how it is useful? If it is not useful, tell why it is not useful.
We need to know that the corrosion is happening.
Yeah. Yeah. So, ICAR by itself is not useful. It cannot give you a direction which of the two will undergo corrosion. First of all, it does not even tell you which of the two will be anodic in nature or cathodic in nature. So, okay, not useful. Okay. I can do a weight loss method, right? I can do a weight loss method. What I can do? I can short both of them, right? And I can determine the corrosion rate, right? I can just short both the metals, determine the corrosion rate. This is time consuming, it takes more time, right? What I can do, if I want to use a Faraday's law, okay, and I just give a clue, right, and I want to find out, what kind of corrosion rate, I just give you half an hour, assume that system is stable, okay. In half an hour times, I want to find out the galvanic corrosion rate. What parameter do you measure? Assuming that the system becomes stable, of course. What do you want to measure? I can measure galvanic current or not? I can measure the galvanic current, can I? Just have metal 1, metal 2, only problem here is I should use a zero resistance ammeter. Huh? Otherwise, what will happen? The ammeter itself will offer resistance, the current flow will be reduced, right. So, use a zero resistance ammeter, you can do that. Okay. So, it is a quick method, it may not take as much time as it will happen in the case of weight loss, but these two techniques suffer one problem. What is the problem? The galvanic corrosion rate depends on what? It depends only on two different metals or depends anything more? Yeah? Of course, that is taken care of here, right? Anything more that will affect the corrosion rate of the active metal? Environment is known, that is given to you, you use the environment only. Yeah? Yeah, tell me what is that? Area is going to change, right? If you are going to change the area, then the rate of attack of the anode is going to be different, right? So, there is going to be one more effect, which is the area effect. So, which means when you do a test, you have to ask a question, what is the area ratio in the actual field? I need to choose that area ratio, otherwise the corrosion rate so measured will not reflect the corrosion rate of a given metal in a given component, right. So, area effect is a very important one. So, you may have to do several tests to find out what happens to the corrosion rate if the area effect is changed, okay. So, that can be circumvented by a simple technique which is called as the electrochemical technique. You can use Tafel extrapolation. I hope you understood what I am trying to say. How do I determine? I say that I carry out only one test for the anode and one test for the cathode, so called cathode, and I use the data for all variations in the area, right? Can I? I give you only one data for anode, I mean so called anode, both cathodic curve and anodic curve, and I give one anodic curve and one cathodic curve for the noble metal. Now I say, hey, please use it for different area ratios. Possible? Not possible. So, I carry out electrochemical experiment, right? I just carry out an electrochemical experiment, scan from one potential to another potentials, I get this, okay. And so, this is the data I get, current density versus this is the data I give it to you. From this, can you determine the galvanic corrosion rate if the area ratios are changed? Assume that the cathode is becoming 100 times more, okay, in terms of area. What happens? So, you would, okay, so what do you do in that case? So, you multiply this by 100 times, right? So, you do not plot high, small I, you plot current here, log current versus this, and so this you multiply by 100 times, it moves over here. Or if the anode is, I mean, sorry, okay, this is metal A in this case is this anode here, but if the cathode, I am sorry, you see, this is the cathode in this case, right? Okay, it's a cathode here, it's an anode here, right? So, you multiply this by 100 times, it moves here. If the anode is 100 times, larger in size, then you multiply this current by 100 times, then you start moving up here. The same curve can be used to determine the galvanic corrosion rate of metal under different area ratios. All you need to do is you need to get only one polarization curve for the different metals, and then you can find out the galvanic corrosion rate of the metals. Okay. So, so much easy. So, what I mean is that this is where you understand how the Evans diagrams, how the electrochemical kinetics will help you in many ways, okay, even testing also, you can make it a very effective testing, okay. And you have any questions? So, with this we will complete our discussion on the galvanic corrosion rate of metals. We saw in the beginning that the galvanic corrosion primarily occurs because of the galvanic potential difference between the two different metals that are in service. The galvanic corrosion does not depend upon the equilibrium potentials, of course. And we also looked at the cases like active metal and noble metal and two different active metals in the passive systems. And we see the electrochemical parameters such as exchange current density, Tafel slopes, the equilibrium potentials, or the factors that control the galvanic potential, the galvanic corrosion current density. Okay. The extent of corrosion depends upon the nature of environment, like how corrosive it is. So, when the environment is changing its properties, you rise the temperature and all these issues, then there can be change in the galvanic behavior. A one metal can turn into the metal which was behaving earlier as a noble metal can turn into active metal. And the other important thing is the fingerprint, the signature of the galvanic corrosion is very clear. It occurs at the anode cathodic interface and occurs at the anodic side. In fact, it is a groove, it is not even a straight one. It occurs straight one, I mean something like that, then there is something more than that actually, okay. Assume that I have metal 1, metal 2, it occurs at the anodic side but occurs fully as a groove, it is not like a, it is not like a V groove, then it is not really, in my view, it is not going to be a truly a galvanic corrosion, there may be some segregation of something happening at the interface. So, the fingerprints of galvanic corrosion need to be understood, okay. The other important area which you need to look at is that if you have a component where you are fabricating with two different metals, the anode area has to be always larger and the cathode area has to be always smaller. And we have also seen how the Evans diagrams can be used to determine the galvanic corrosion rate of metals with a simple experimentation. And with this we will end our discussion on the galvanic corrosion of metals. In the next class I think we will go on discussing about the crevice corrosion, okay. So, thank you very much.